Hello and welcome to this Bentley Success Factors webinar. My name is Jake Hanna. I'm a naval architect, structure engineer and senior software engineer with Bentley Systems. Today I'm going to talk to you about some of the structural design and analysis tools for marine structures that we have available. I'm going to spend the first part of this webinar looking at how we can export ship structures from our naval architecture design tools in MAXSURF and import them into our structural tools in MultiFrame. And then the vast majority of the webinar I'm going to do some demonstrations in MultiFrame on how we can enhance those structural models with some advanced plate meshing tools, some of which are particularly specific to the marine environment, and then apply the environmental loads onto that model ready for structural analysis. I would now like to demonstrate how we can export structural information from MAXSURF into MultiFrame. And then in MultiFrame I will do a demonstration of some of the more advanced plate meshing tools that we have available, particularly those applicable to the marine environment. Okay, so here we are in MAXSURF Modeler. I'm going to open up one of our sample files, which is that of a workboat. And as you can see, this has some structural information defined in it, namely frames, bulkheads, decks, and in this case stringers. I've left off the hull plates just so you can see a little bit of clarity throughout the model, but these could be defined as well and added to the MultiFrame export. For those of you that are long-term MAXSURF users, you previously would have done this sort of definition in MAXSURF structure. However, we've recently merged this functionality into MAXSURF Modeler, and you can see the menu items here that you might be familiar with from structure. It's simply a consolidation of our applications. All of the functionality is still there, but it's all now contained within MAXSURF Modeler. I'm not going to spend any time in this webinar showing how you define this information, the frames and things like that. That really is a subject for a webinar on its own. The focus of this webinar is more of the MultiFrame end, creating the FE mesh and applying some of the marine loads to that. Without further ado, I'm going to show you how to export that to MultiFrame. So from the File menu, the Export option, then the sub-menu for Structure, you want to select the MultiFrame text file option. You're then prompted for the default FE mesh size to export. The trick here is to go for something a small enough mesh that you still preserve all of the detail of any curves, and obviously there will be lots of curves in your vessel models, but not too small that the export file becomes too big and there's a danger of introducing errors in that format. So the default option here of 0.08 meters works pretty well for this model, so I'll just run with that. Select a file name and my text export is complete, so I can switch over to MultiFrame, and in a similar way from the File menu, if I choose Import this time and then MultiFrame text, I can import my workboat text file which I've just created, and you can see all of that information that we had there, including the stringers that we had defined in MAXSURF, has now been imported into a MultiFrame structural model. It should be noted that stringers are linear between upstands, where one upstand is at each frame along the stringer. So it might be sensible to add dummy frames where there is a lot of longitudinal curvature on your vessel to get a more accurate stringer shape. I would just like to break away from the MultiFrame demonstration for one moment to make a couple of comments about the respective axis systems in MAXSURF and MultiFrame. They are different, and these differences can become particularly apparent if the model is not symmetrical. As you can see in this table here, for MultiFrame we have X positive in forward direction, which is actually the same in MAXSURF, but the Y's and Z's are reversed. Y is the up direction in MultiFrame, whereas Z is up in MAXSURF, and vice versa to the direction to starboard. It should also be noted that MultiFrame is a right-hand axis system and MAXSURF is a left-hand axis system. Right, as I go through this webinar, not only am I going to show you this marine functionality, but I'd also like to give you a few MultiFrame hints and tips. I suspect that quite a lot of the people listening in on this webinar today might be quite familiar with MAXSURF, but not so familiar with MultiFrame. So if I can give you any tips on how to use MultiFrame, I think that's going to be advantageous as well. And the first of those tips is how to manage a 3D model like this. This is a relatively complex model, but still quite small. Likely you'd be doing bigger models than this. And it's really quite hard to see exactly what you're doing to select the right thing you want, whether you don't know whether you've clicked a deck or you clicked that bulkhead it attaches to. And one of the good ways that we can chop this model down into bite-sized pieces that we can look at is using the clipping tool. So from the view menu, if we choose clip to invisible and then go to one of our 2D views, we can see that there's a dotted line all around this, and anything that lies outside of that 2D line becomes invisible. It still exists in the model, but we can no longer see it. It's no longer confusing us. So if I drag this dotted line aft a bit, we can see that all of that bit of the model disappears. And if I drag the other one forward, all I now have that is visible is that one bulkhead. Nice and easy now to select that and edit that without being confused by all the surrounding structure. Rest assured the rest of the model is still there. If I was to change to clip grey, you can see it there. But I'm just going to go to invisible because it makes things even easier to see. Alright, from a front view, I now want to, so as we can see, we've brought in the geometry of this bulkhead fine from MAXSURF, but I want to add a little bit of detailing. In this case, first of all, I'm going to add an opening to this bulkhead. There's a number of tools in MultiFrame for adding openings. So from the frame menu, the sub-menu of add opening, there's 4 types: rectangular, rectangular with rounded corners, circular, or any number of end sides. I'll go for ones with the rounded corners. Just click and drag to where we want it and define that radius that we were talking about. Now, this patch opening is more than just a hole in the patch. It is actually an object in its own right, and I can select it, and it has its own set of properties. In MultiFrame, if you select any object and then right-click, you have a pop-up menu and it shows you what commands are available. In this instance, I'd like to extrude some rider bars on my opening. I'm going to choose the direction that I want to extrude them in. That's the direction relative to the local axis of the patch they're attached to, and then give them a width. Go back to a 3D view, zoom in nice and close. You can see that patch elements have been created all of the way around the opening, including following around the radius of these corners. Doing this manually would be quite a tricky and laborious thing to do, so that extrude rider bar tool is a nice one there to save you a little bit of time. Those of you familiar with MAXSURF structure will know that you can actually add openings and rider bars in the MAXSURF model before you export it to the MultiFrame via the text export. What's the advantage of adding openings and rider bars in MAXSURF over MultiFrame or vice versa? It's really up to personal preference here, I would say. There's a few more default options in MAXSURF for different shapes of openings, probably versus at this point the meshing capability of MultiFrame is slightly better. I would say that use probably add these openings in the tool that you are happiest using. If you've used a lot of the structural functions in MAXSURF, then you're probably happier doing them there. If you like the way that MultiFrame does this sort of thing, then use MultiFrame. Okay, you can see the faint lines within here, which shows the individual plates which make up our FE patch. If I select this patch, I can change the meshing. Again, I've selected it, so I can use right-click, patch meshing, and let's make that mesh size much smaller. And you can see I've got a much more detailed patch mesh. This mesh is continuous over to adjacent patches. The boundary of these patches is defined by where a deck intersects, and all the patches, you'll hear me referring to this a little bit, is a collection of plates which all share the same, a plate being an FE element, the same material properties. Obviously on this bulkhead we're all talking about the same material, the same thickness, and it makes a much easier way for you to select them and then edit those properties. Yes, and you can see where this patch adjoins the next one, we've got a continuous mesh there, and the edge of that one has been remeshed, and that's continuous throughout the model. So I've shown how we can edit the patch, the density of that mesh just in one patch, or I could select the whole model and change that density. The next thing I'd like to do to this bulkhead is add some stiffeners to it. Again, selecting and then right click, we see they've got a command here to auto generate some stiffeners. Choose the stiffener type. We've got some marine sections which are supported in MultiFrame, and I can choose its orientation and whether it's on the top, the front or the back of the bulkhead again. And there's some different options here for the direction that they run in, including you can run them at a diagonal angle as well. I'll just have mine running vertically, and let's reduce the spacing down quite a lot. And then if I click OK, you can see the stiffeners have been added as beam elements and the patch has been remeshed. The really nice thing about this is that it deals with the diagonal edge here, so we've got a stiffener that ends there. And equally the opening, so they go up to the opening, not across the opening and starting it on the other side. Again, an automated tool which is going to save you a lot of time adding something manually like that. Another way that we can deal with the effect of stiffeners on a plate is by changing the material properties. Within MultiFrame we also support orthotropic materials. And orthotropic materials are really useful if you've got different material properties in the two different directions, the sort of the X and Y local directions of a plate. I'll show you how to do that if you select a different patch. And then if I go to the patch properties, within the material area here, I'll just highlight that. There's an advanced button. Click the advanced, and there's two different ways to do orthotropic. One of them is if you know the value of Young's modulus Poisson's ratio in the two different directions, the local X and local Y of that plate, you can define those yourself. Or if, how the example I've done here, you have got the equivalent stiffener on a plate, you can define exactly what those stiffeners are. As before, I can select my bulb flats, and then MultiFrame will do those stiffness calculations for you. That's just how you can use orthotropic materials. Okay, moving away from modelling hull models themselves, I'd like to talk about some of the other tools available in MultiFrame that are available for naval architects such as yourself to solve structural analysis problems that you might come across. The first of these tools is how to apply sea motion loads. Sea motion loads are the accelerations on a structure due to the motions of a vessel. This tool allows the motion-induced loads on the structure that might be fastened to a deck, say in transit, to be calculated automatically. Okay, so switching to MultiFrame, I'm first of all going to create a very quick and simple structure that might be on your that you might be wanting to fasten to your deck. MultiFrame has got a tool here where we can calculate a number of different types of structure automatically. I'm going to go for a frame. Just enter the number of bays and stories and spacing very quickly, and here I've created a 3D structure. Okay, let's just give that some section properties, not too fussy what they are, and we'll apply some restraints to the bottom of it where this structure is attached to the deck. And the last thing that I'm going to add to this structure is a couple of what we call joint masses. Okay, so joint masses aren't actually physical parts of this model, but they might be something that's on your model, in your frame, which you don't want to model because it has no structural strength itself, but could be a piece of equipment or a part of it that has a mass and thus is going to have some accelerations due to gravity and due to any motions of the vessel, and is thus going to apply loads onto your model. So I will apply a reasonably heavy couple of joint masses right in the center of my frame. Okay, the next thing I'm going to do is bring in a little bit of background geometry so we can place this structure. So if I just switch back to MAXSURF, I'm going to open up a model here, a MAXSURF model here. I've got an offshore supply vessel, which is typically the sort of vessel that might be doing this sort of work. Just allow that to open and render properly. There we go, here we go. Here's our MAXSURF model of my offshore supply vessel. And rather than doing a multi-frame text structural export this time, I'm going to export it as a DXF file. And the settings I want for that is a 3D file, and it's the mesh that I'm interested in. Okay, I can export that. Switching back to multi-frame, I can then import this. There's a couple of ways we can import DXF files in multi-frame. We can import them as straight away as beams, as members themselves. We can import them as something we call construction lines, which is not actually a physical structural thing, but it creates the points to click together and click on to maybe add some structure yourself. But the one I'm interested in this occasion is the background DXF. Select my model. Okay, before I do my import, I need to set the axis system that this is being brought in, just to make sure that up in MAXSURF is the same as up in multi-frame, and port and starboard and forward and aft the right way around as well. You can set your own settings here, so if you're importing DXF files from a different system which uses a different access system, instead of messing around and trying to work out what it is every time, you can add a set of settings yourself. So for each time you do the import, all you need to do is select them and it's done. The one I need here is background DXF, and there it is. Here is my background image of my offshore supply vessel that we saw in MAXSURF. Okay, so I just need to place my structure onto the deck of this offshore supply vessel. It's just done in the 2D view. I'm not going to be very scientific about this, just place it roughly in the right place. There we've got the right height. Switch to the top view and just move it there. Let's put it roughly in the middle, shall we? Okay, great. There it is. There is my structure I've created, made out of members with some joint masses in, some constraints on the bottom, placed on the rear deck of a vessel. Now to apply some loads which correspond to the sea motions of that vessel. Okay, switching to the load window, and the load case that we want to apply is the sea motion load case. I'm just going to jump out of MultiFrame for a second and explain a little bit about some of the inputs in this dialog because they are reasonably complicated. Here you can see an expanded view of both the dialog and the diagrams that go along with it. I'm going to walk now through these inputs. Top of the list is the just a name which you can give to your load case and helps you organise them for later reference, particularly when you end up with a model with lots of load cases. And then the next one is the linear accelerations. Combinations of surge, heave and sway can be applied by entering values in these boxes. Surge is applied along the x-axis with forwards positive, heave is applied along the y-axis with upwards positive, and sway is applied along the z-axis with starboard positive. All of the accelerations to be input in this dialog can of course be calculated in MAXSURF motions. If the vessel has a static trim, this can be accounted for by specifying a pitch rotation, and similarly for a static list angle which can be specified as a roll rotation in these 3 rotation angle boxes. Angular accelerations can be applied, and these act around the centre of motion of the vessel, the location of which is defined by the motion axes. Roll is applied about the x-axis with the starboard side down positive. Yaw is applied about the y-axis with bow to starboard positive. And pitch is applied about the z-axis with bow up positive. The location of the motion axis with respect to the origin is defined in the motion axes boxes. The x direction is positive if the model's origin is forward of the centre of motion, the y direction is positive if above the centre of motion, and the z direction positive if it's to the starboard of the centre of motion. It is possible to include the self-weight load case within the C-motion case. The reason for doing this, instead of creating a combined load case made up of a C-motion and a self-weight case, is because linear accelerations due to gravity will be adjusted for any rotation angles entered. To include the self-weight of the structure in the C-motion load case calculation, tick the Include Self-Weight checkbox. If this was a little bit complicated, don't worry, all this information is in the MultiFrame manual. Alright, okay, so I've talked about these. Now I better add some values, some reasonably arbitrary numbers. Let's apply some surge. Let's roll the vessel a little bit. And why not? Let's have it pitching as well. And these are quite important. As I said, these distances from the origin to calculate these lever arms. Vertical and transverse, let's say it's on the centre line. Okay, there we go. Like I said, I'll just leave joint masses for now. And there we can see we've got lots of loads which have been calculated on the structure due to the accelerations of the C motion. Each member there on the model has got 2 loads in 2 directions. So if you would have to calculate all these by hand, yourself in a spreadsheet, then apply them to MultiFrame, that's obviously going to be a reasonably time-consuming process. These, as I say, they're all distributed member loads at the moment. If I go back and I edit my load case, and this time I tick my joint mass button there, you can just about see, it's a little bit of a mess underneath all the distributed loads. Maybe if I zoom in, we also have some joint masses here, some point loads here on the vessel due to those joint masses. Okay. Now, if we do a linear analysis of this model, then go to our plot window to see the results, we can see the bending moments on the vessel and the reactions due to these C motion loads. The deflected shape, calculated stresses as we would for a normal multi-frame analysis. The next load case I'd like to demonstrate to you is the hydrostatic load case, which automatically applies hydrostatic pressure due to fluids on a structure. The first structure which I'm going to apply loads to is a tank. In my wizard here I can quickly generate a circular tank, tall and thin tank. I'll just give it some material properties, and now I can start applying my load to it. Okay, from the case menu, add case, and this time the hydrostatic load case. We've got a couple of options for the fluid height that we add. We will just go with a flat water level for this case. I can define the density, and I can define whether the fluid is inside or outside the structure. In this case I'll go with fluid inside the structure, as if it contains a fluid. If the fluid was outside the structure, it would be a vessel submerged into a fluid, like a ship floating in the ocean. There's two different model types for this load case. One is a 2D cross-section made of members. The other is a 3D model made of patches. MultiFrame has already detected that I only have patches in this model, so it's selected the correct one for me. And the final thing I need to do is to find an internal point within that structure, just to make sure that all of the pressure loads go in the right direction. That is, if it was a fluid inside the structure, I want all of my loads pointing outwards, and vice versa for external. This is a nice uniform shape model, very uniform shape model, so the centre of gravity is a great guess and the correct guess for that internal point. If it was an unusually shaped tank, the centre of gravity might not actually be inside the structure, and you might have to mess around a little bit and use it to find something which is in the correct direction, just to get all those pressure loads in the correct direction. Okay, there we go. We've seen we've got pressure loads applied to the model. There's a little visualization of where the water level is, and you can possibly see that as the water gets deeper, the pressure loads increase, i.e. those blue arrows get a little bit bigger and a little bit darker, as you would expect for the calculation of hydrostatic pressure. Okay, so I'll now do a demonstration of a 2D hydrostatic problem. I'll open up a model I've got here already, and that is the cross-section through a fairly regular shaped barge. And to this I want to apply the hydrostatic pressure of the water outside it. So again, I'll add a hydrostatic load case. This time I'll use a sinusoidal waveform just to demonstrate that. Fluid density is fine at seawater. This time the fluid is outside the structure, and MultiFrame has correctly selected that this is a 2D cross-section, members only model, and the tributary area, which is typically the frame spacing, is the distance which these pressures are applied upon. Let's increase that a little. Again, we've got this idea of an internal and external point, and again the centre of gravity is a perfectly acceptable guess for that in this situation. So there you can see my waveform shape pressure, and along the bottom of this hull you can see that actually that pressure that MultiFrame applies varies as it goes up and down through the troughs of this somewhat exaggerated wave, and that it decreases as you get to the surface up the sides of the vessel. One problem you can see automatically is that not only have we applied the hydrostatic pressure loads to the hull of the ship, but they've also been applied to the internal structure, which obviously we don't want because that's not the case in real life. And I'll just show you how we can quickly remove those. If we select them, and the easiest way to select these is to do a right to left selection, which will select all of the intersecting members. And then if I click right click, which will give me the options available in this situation, and click my hydrostatic members, I can either switch the direction of them, so if we've got that internal point wrong we can individually change the loads, or in this case I want to ignore them completely, And there we have our model corrected to show exactly where we want the hydrostatic pressures applied. And now I'd like to demonstrate a few more of the environmental load cases available in MultiFrame and how they can be combined on a simple but realistic model. So here we are in MultiFrame again, and I've just got modelled a small tower. This tower is anchored to the seabed, and it's in around about 5.5 metre depth of water. I'll show you what it looks like in the render view. It's made of tubulars, slightly larger tubulars on the legs and some smaller ones for the cross beams. Now I'm going to start applying some loads to this structure. The first one I'm going to add is a self-weight case, which is just due to the weight of the members themselves. So the acceleration we're applying to the model is gravity in the negative y, downwards direction. And you can see the loads, distributed loads on the model for all of those, with obviously the slightly larger forces on the larger legs. And then in the opposite direction to the weight acting down is the lift force due to the buoyancy of the water underneath. As before with the hydrostatic load case, we can apply a flat waterline or a sinusoidal waveform. I'll keep this one relatively simple with a flat waterline, and as I mentioned, the water depth is 5.5 metres. We're in seawater, so 1025 kilograms meters per cubed, and again gravity we can set ourselves as well. And we have in here an option to flood hollow members or not. If we tick flooded, then we're only going to get a lift force equal to the volume of steel underneath the water. If I was to not tick that and not flood them, then we're going to generate a lift force due to the whole cross-sectional area of that hollow section. Obviously this only applies to hollow section, but we do have hollow tubulars in this model. I'll show you in just a second how we can have a combination of flooded and unflooded members in the same model, so I'll leave that unticked and I will not flood my members. Okay, so now you can see our distributed vertical upward lift force, but only applied below that flat water plane there at 5.5 metres. As mentioned, I want to flood some of my members but not others, so I'm going to flood the larger leg members. These are the green ones, the HSS8s, and if I double click on them in this legend in the top right hand corner up here, it selects those ones for me. And as before, right clicking, I get my member buoyancy dialog. And I can click flood for those, and they will be flooded, and whereas the blue cross beams will remain unflooded. And as you can see, when I did that, it significantly reduced the size of those distributed loads on them acting in that vertical direction. Right, the next load case to apply is going to be some water current. And this is applied obviously only below the water level as well, so if we add our water level at 5.5 metres, that'll cut off and not apply water current to anything above that. And we can add a velocity profile which could be constant or might vary. Let's have this increasing a little bit as we get towards the surface. Again, water density, and we can apply direction. 45 degrees, this direction is in reference to the global XZ axis, and MultiFrame automatically calculates a set of pressure coefficients. You can override those with your own preferences if you wish, but we'll just go with the defaults. And here you can see our range of water currents, which is lower at the bottom on the bottom and higher near the surface, being applied as distributed loads again on these beams. There's 2 loads per beam due to the fact that it's applied in the 45 degree direction, so one in the local X and one in the local Y on each member, and no loads above the waterline as we would expect. One final load case to add to this model and that is a wind load case, which is obviously the opposite to the water current, and it's going to only apply above the water line. We don't have a way of defining the water height for this one, because this is more of a generic load case, probably more commonly used when designing buildings on land, but we can do some clever things with wind velocity profile here to make sure that there's no wind applied to those members below the waterline. Of course, obviously we could apply wind to the whole of the model, select those members below the waterline and ignore those for this load case, but I'm going to do it with a velocity profile. So I'll add a couple more rows to it and then set my heights. And have everything from 0 to 5.5 meters as 0, and everything from 5.5 meters to 10 meters in height as 25 meters per second. As before with the water current, really the same principles apply, but with a much slower density of our medium which is being applied. We can then set the wind direction in the same way that the water current could be applied. Obviously it doesn't have to be in the same direction, and we can choose a few options whether to include members and patches in these calculations, and auto calculate factors again. The coefficients in this wind load case are based on the Australian standard AS 1170. For those of you not in Australia or elsewhere in the world, you can again manually apply your own pressure coefficients. Okay, so let's apply the wind load case and see what that looks like. So as expected, we have got no loads on the structure below the waterline, but we do have loads on the structure above the waterline. Right, so now we've applied self-weight, buoyancy, water current and wind individually, and what we'd like to do is combine these all in one load case, which is really what's going to happen in real life. So we do that by adding one more load case, which is a combined load case, and let's change that name just so we can see a little bit more which one it is, and we can add factors of these load cases that we've added already. If we can 0 and it won't be included at all, 1 and we get 1. If we put a factor of 1.0 in, we get 100% of that load case, and everything in between. Obviously the factor could be more than 1 as well. So we'll do 1.0 for self-weight, 1.0 for buoyancy, but we'll increase our water current and wind a little bit. Okay. And then you can see lots and lots of loads all over the model because we've combined 4 different load cases there with those factors combined. Alright, let's run a linear analysis of this model. Okay, now we can look at some results. Switching over to the plot window, what we see here on the shape is the bending moments in each of those beams. I can also show the shear stress, the axial loads, and the deflected shape. The deflected shape looks a little bit better in the rendered view, where we can see the actual size of the members, and the colour chart shows what the size of that deflection, so we can see which are deflecting the most. This is all for the combined load case, but we can see the load cases individually if we should wish. The self-weight there. Buoyancy, pretty small, just a little bit of deflection at the bottom. Our water current. The wind load case. Then back to the combined thing. And then finally, just a nice little thing to do, is we can animate these results. And that brings me to the end of this presentation on the structural response of marine structures. My name is Jake Hanna, and thank you very much for attending.